Okay, this video is covering 4.6 optimization problems. This is another word problem section, and we will be using our skills that we just practiced with the first derivative test in order to answer these word problems. So this week is not a PowerPoint, it is a Word document with some examples on there. I thought this might actually be a better way to do it than a PowerPoint form, since I do all the solutions for you out anyway. So our very first problem is a rancher has 400 feet of fencing for constructing a rectangular corral. Essentially, a corral is what holds the animals in. One side of the corral will be formed by a barn and requires no fence. Three exterior fences and two interior fences partition the corral into three rectangular regions. What dimensions of the corral maximizes the enclosed area, and what is that area? Okay, so key word here is maximize. We just learned about finding maxes and minimums in 4.2 and how we use the derivative and set it equal to 0 to find those. So the moment that you see the word maximize in a word problem or minimize in a word problem, you think optimization, you think derivative, set equal to 0. That's where your mind needs to be. So I see the word maximize. I know I need a derivative of a function that I need to set equal to 0. Now it's all about what the heck is that function that I need. So let's find some other key information. There's 400 total feet of fencing. Okay, so if we're talking about the amount of fencing, there's 400 feet of it. So think perimeter. And we have a picture here to help us with the interpretation of the words. That is not guaranteed on these word problems. In WebAssign, there may or may not be pictures. So use these examples that I have pictures drawn for you today to help you with the English translation into what the heck that looks like as a picture. Because if you draw the wrong picture, you could very easily do the wrong equation and go in the completely wrong direction. So with this picture, the 400 feet total of fencing and the fact that we are maximizing the area in these corrals where the animals are going is what we need in order to come up with an equation. So again, what's important is we're maximizing, and we probably should highlight this word too. What are we maximizing? Area. Whatever it is that we are maximizing or minimizing is what needs to become the function that we write, because that function we are going to take the derivative of and set it equal to 0 to find that function's max or mins. So you want to make sure that we do take the derivative of the correct function. So let me draw a quick picture so we have reference. So we have the barn, and then using that barn as one side, we create a corral with two interior fences and three exterior fences. Okay, and the barn is the back of the corral, so we don't need any fencing there. So the orange is the fencing that we need. So we need to label this, okay, because we're looking for maximize area. Maximize area. Okay, so that's the stuff inside of the corral. So if I'm maximizing area and I'm looking at a rectangle, my area of a rectangle is length times width. Well, that makes perfect sense. Length times width is how I find an area of a rectangle, any given rectangle. This happens to be a rectangle divided evenly between three other smaller rectangles. So the length of these sides, let's let the length of these sides be x. So this piece of fence is x in length, this piece of fence is x in length, this piece of fence is x in length, and this is x in length. They wouldn't be different lengths because this has to match up with all of them. And we don't know that this piece is the same as the 4x's, so we will label that y because it may be different. That would be this length here. Okay, so if we are looking at ideally building an area formula, we need to think about what we know. Now, we do know that area is equal to x times y, length times width, to maximize the area in this corral. But we don't know x, and we don't know y, and we don't know area. So three unknowns with one equation is not a good start. So we need to know something else. Remember, if we went back to the PowerPoint, the numbers we highlighted. We highlighted a 400, but the 400 was not the area. The 400 was the amount of fence. How can we write an equation for the fence? For how much fence? All right, well, let's think about this. We have 400 feet of fence, and we have X amount of fence used on this left side, plus X amount of fence used in the first interior, plus X amount of fence used in the second interior, plus X amount of fence used in the exterior on the right side, and then plus Y, which is this front part. That all added up, 4X's and a Y, should add up to the 400 feet of fencing. Hopefully you guys agree. So that means that I have these two formulas so far. I have that area is equal to X times Y, and I have 400 is equal to, now there are four of those X's, so I'm going to write 4X's plus 1Y makes up 400. Now, when we have two equations and we have two unknown variables, ignoring the area, because we don't know the area, we're going to find that last, then we should do a substitution. So if we subtract 4x on both sides, and we get y is equal to 400 minus 4x, then we can make a substitution in our area formula for y. Since y is equivalent to 400 minus x, let's substitute this 400 minus x into the area equation for y. Now that gives us an equation in terms of x, which is a very helpful place to be. Okay, so now that we have an equation for area in terms of x, let's simplify first. So let's distribute this x in, and we have area is equal to 400x minus 4x squared. Okay, let's find the derivative of area. So a prime, derivative of 400x is 400. The derivative of negative 4x squared is negative 8x. We learned in 4.2 when proceeding to find the maximized area or minimum, critical values, we have to set this derivative equal to 0. So we take this derivative and we set it equal to 0. So we have 0 is equal to 400 minus 8x. And solve for x to get our critical values. So let's subtract 400 on both sides. And we get negative 400 is equal to negative 8x. Let's then take the negative 8 and divide on both sides. So a negative 400 divided by a negative 8 gives us a positive 50. So x equals 50 feet. Okay, now we need to find y, or more importantly, now that we know the critical value, remember this is the critical value, so something's happening at this point, and as we learned in 4.2, we know that this could be a max, a min, or an inflection point. And the only way to verify that this is a max, not a min, not an inflection point, is to run our first derivative test. Okay, so let's now run our first derivative test. On what we just found. Okay. So we have a critical value of 50. You need a test point on the left and a test point on the right. So I'm always going to choose easy test points when I can. So my test point on the left side is going to be 0. Not really an easy one on the right side. I'll just pick something simple to look at. So I'll pick 100, but I could pick anything. I could pick 51 or 50.1, anything on the right side. And remember, we have to put these values back into the derivative, because if the derivative is positive, we know the original function is increasing. If the derivative is negative, we know that the original function was decreasing. And that's important for us to know what's happening before the 50 and after the 50 to determine whether it is a min or a max. So let's find the derivative at 0. Okay, so we have 400 minus 8 times 0, which comes out to be positive 400. So since it's positive, then that means that we are increasing on this left side. So it's looking like the 50 is either a max or an inflection point, because if we put the 100 in and it's also positive, then it's an inflection point and it's a change in concavity, but it is not a max. And that would be important to know. So let's now put the 100 into the derivative. So we get 400 minus 8 times 100. Okay, so 8 times 100 is 800. 400 minus 800, all that matters is that it's negative. So negative means that we are decreasing. We can see, okay, the 50 is creating a top peak. This 50 is a max, which is good because it was the only critical value that we found. And if that was not a maximum, we would not be able to answer this problem. So now we know that to maximize the area, the x is 50 feet. So now we just need to find y. And we do that by using the original equation. So we have the y equals equation. It's already solved for y. Actually, believe it wasn't that. It was 400 minus x. Sorry, 400 minus 4 x's. Those 4 x's plus y is equal to 100. We move that to the other side. Yes. Okay. Let's substitute the 50 in. So y is equal to 400 minus 4 times 50. Okay, so we put that in our calculators, 400 minus 4 times 50, and we get 200 feet for y. So now we know to maximize the area, the dimensions. So the first question is that it's a 50 by 200 corral. And the area would be 50 times 200. Second part of the question asks us, what is that area? So 50 times 200 gives us 10,000 square feet. Okay, that's our first optimization problem. Let's move on to the next one. Okay, our next problem. Suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of a square-based box with the greatest volume under these conditions? Okay, well, let's highlight some important things that we have found here. We see that we are talking about a box shape. Okay, that might not be that helpful. Square-based box is important because square-based box tells us that the width and the length are the same. Notice that in my labeling, I already showed that. So I'm trying to highlight that the width and the length are both the same. So we can label them both W's, or we could have labeled them X's. X's might not be a bad idea, but this is fine. So we have a width by width, because if you think of a square, the length and the widths are the same. So that was important that they're the same. Now the height is whatever, we don't know. volume for a cube, not a cube, for a rectangular box is length times width times height is the typical volume formula. So if I wrote that prior to this one, I wrote volume typically equals length times width times height, then it might be easier for you to see where we got the formula that we'll be using, which is this one. Okay, because length and width happen to be the same. It's width times width, which gives us W squared. So that's where we got that volume formula from. Really important. Now we have to take a look if there's, remember this is 3 unknown variables in one equation that we are looking to maximize greatest volume. Okay, so we want to maximize this equation. So this is the one we're taking the derivative of because that's what it tells us. Maximum or greatest volume. Volume gets the derivative, which means there has to be some other equation that we know because remember, we need this to break down to in terms of W or just in terms of H, but it can't be both unknowns. So we look back up here for some more information and I see that the height cannot exceed 64 inches. Oh, wait, I got to go back farther. Sum of length, width, and height cannot exceed 64 inches. So we need to use that to come up with another equation. So let's build another equation. And let's see, length plus width plus our height is not exceeding, so it needs to be less than or equal to 64. So that's important. Now, if we think about what we're doing here, we are talking about greatest volume. So would we want the length, the width, or the height to be smaller than we can possibly make it? No, we're trying to maximize the volume. So we know that because we're trying to, this is a maximize problem, we're trying to maximize that we don't want this to be less than or equal to. We will make this an equal to sign because we are trying to find the largest volume. So with that, let's head back to the whiteboard and try to come up with our equations. Well, we already have the equations, but let's try to solve these things. Okay, so we have that the volume is equal to W squared because there are 2 widths and a height. And we have that the length, which is also the width, plus the width plus the height is equal to 64 because less than 64 is not going to help us with maximizing. So since the length is a width, we have 2W, so 2W plus H is equal to 64. And again, how do you know which one of these equations you should be taking the derivative of? And it has to do with the wording of the problem. The wording of the problem said to get the greatest volume. So that means that we are taking the derivative of the volume formula and we need this extra equation to help us with substitution. So since H is by itself, I'm going to subtract 2W on both sides and I'm going to get H is equivalent to 64 minus 2W. I'll come over here to my volume formula now, and I will make a substitution for height and replace it with its equivalent expression in terms of W, which is 64 minus 2W. Now, I could go straight into taking the derivative, but right now I have a product rule, and I like to make my life a little easier. So if I just distribute this in and create a straight polynomial, my derivative will just be simply power rules. So I have the volume formula is 64W squared minus 2W cubed because we have a W squared times a W. Now the derivative of volume is going to be 2 times 64, which gives us 128 W. And we have 3 times -2, which gives us -6 W. Go back up, subtract 1 from the 3 squared. So that is our derivative formula. And now we are going to go to the next step of this process, which is to set the derivative equal to 0. So we have volume prime is equal to, we came out with 128W minus 6W squared. Set it equal to 0. And I see that I have 2 different terms. One's a W term and one's a squared term. So I'm going to factor out a W. Let's see if 128 is divisible by 6. It's not. It's divisible by 2, so I can take a 2 out. It is not divisible by 3. So I'm going to take a 2W out. So let's factor out a 2W, which leaves us with 64, because we took out half of the 128, which leaves us with 64. And we took out the W, so no more W. Take out half of the 6, which is 3, and took out one of the 2 W's, leaving us a W inside. Now, as we practiced with our 4.2 with max and mins, we saw that at this point we have a 0 product property where we have 2 things being multiplied and set equal to 0. That states that one of these 2 things must be 0 in order for a product to result in 0. So we set each one of these equal to 0. Divide by 2, divide by 2. I get one critical value is W equals 0. The other critical value, we have to subtract 64 on both sides. So we get -3W is equal to -64. Divide by -3. I don't have room to write it, but divide both sides by -3. And we have 64 divided by 3 gives us a width of approximately 21.33 if we did not keep it exact. We could keep it 64 over 3 if we wanted to be exact. Now, to me, the 0 is unimportant. I don't even need to entertain the 0 because if the width of the box was 0, that's obviously not going to maximize volume. That means you have no box. No box, no volume. Not really helpful. So now our focus is on this 21.33 because again, we know it's a critical value, but we don't know if it's a min, max, or inflection point. So we need to do our first derivative test. Okay, so we set up our critical value of 21.33. It's repeating. That's our critical value. Again, we don't care about the 0 because that's not going to maximize anything. I'll pick a test point on the left side to be 0. Test point on the right side, I'll pick 25. And let's get it done. So we have the derivative of volume is equal to, and that was 128W minus 6W squared. So we are putting in, for our first test point, 0. Well, that's easy to calculate. That comes out to 0. So what does that mean? Well, that means that 0 is also a critical value. That 0 is an inflection point that we oh no, it's a critical value. Oh, darn me. 0 was the other critical value, so we can't use that. It's not going to tell us positive or negative because it's one of the critical values. It's a min, max, or inflection. So unfortunately, I can't use my easy 0. I have to use something else. So I'm going to use 20. Okay, let's try this with 20 this time. So if we put this in our calculators, 128 times 20, subtract 6 times 20 squared, and we get a positive 160. Again, who cares that it's 160? What matters is that it's positive. So we are increasing. So far, we're looking good for a maximum value here. But again, we can't be too sure because it's also possible that it is an inflection point. So let's now put in our other test point on the other side, the 25. 25. Enter this into our calculator. So we have 128 times 25 minus 6 times 25 squared. And that gives us a negative 550, where the 550 is unimportant. We care that it's a negative. So we do indeed have a maximum critical value at 21.33. So we know that the bottom, the square part of the box, needs to be 21.33 by 21.33. So let's take a look at that. So we have a square base box. My box is on its side because I'm not the best drawer. But this square W by W is 21.33 by 21.33, or to be exact, okay, 64 over 3 is the square of the base. Now we need to know what the height is. Okay, so if you recall, we have a height formula that we solved way back in the beginning. We have that height was equal to 64 minus 2w. So let's put this w in. I'm going to use the exact value just to make sure I'm getting the right value out of this height. So I have 64 minus 2 times 64 over 3. Okay, now let's solve this out. So let's just put this in our calculators. So we have 64 minus 2 times 64 divided by 3. And we get 21.33. So that is also 64 over 3. So what is this saying? This is saying that in order to maximize the volume, you actually need a cube. You need a length times width times height are all equal to each other at 64 over 3 feet, or 21.33 feet approximately will maximize your volume. All right, let's head on to the last example of this section. So our last example is a man launches his boat from point A on a bank of a straight river 3 kilometers wide and wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. He could row his boat directly across the river to point C and then run to B. Or he could row directly to B, or he could row to some point D between C and B and then run to B. If he can row 6 kilometers per hour and run 8 kilometers per hour, where should he land to reach B as soon as possible? We assume that the speed of the water is not a factor, which is not realistic because if this was a river, there would be some current rate. And whether we were against the current, which would slow down our overall time, or with the current, which would increase our overall time, that would actually matter in a problem like this in the real world. But in our case, we are only working with a still river. So I guess we should pretend that this is more like a pond or puddle with no current whatsoever. Again, not particularly that realistic. So important things that we need to label in our picture is that from C to B is 8 kilometers. So we would want to label from C to B with 8 kilometers. So let me get a brackety tool here. Oh, what the heck just happened? Not what I meant to do. Okay. Oh, here we go. Whoop. Okay, from C to B, we have 8 km. Bigger so we can see it. All right. C to B is 8 kilometers. The other thing that we need to recognize is that the width of this river was stated to be 3 kilometers. Okay, so picture that to be from the left side of the river to the right side of the river that doesn't have a current. And we need to label X. So because D is an undetermined point, so B is set 8 kilometers downstream, C is directly across from A, but D, they're saying D is anywhere here in between where we should stop. Maybe there's an optimal point between. Okay, so we're going to label the distance between C and D to be distance X. Because again, we don't know how far from C D is, if that even happens to be something that we need to consider of stop rowing some point down the river and then run the rest of the way. All right, so this one has a lot going on, but we have a great picture now. Let's jump on over to this whiteboard and try to figure this out. Okay, let me draw this picture for us in front of us. We have the left side of the river, the right side of the river. We have point A, which is where we're starting. We have 3 points along the river. So we're starting here. We could go directly across the river. We could stop somewhere between where we are and our destination B. Okay, so this is one way we can go, another way, last way. We label what we know. We know the width of the river is 3 kilometers. We know the length that we need to travel, 8 kilometers downstream, and we are letting the distance between C and D be X. Okay, let's actually write that out. We are going to let X represent the distance between C and D. So how far are we going down before we start running? Okay, so if we look at the distance, abbreviate it dist, the distance between D and B. Okay, so wherever we stop, what is the distance here? That's what we want to know. What's this distance between where we stop rowing and where we start running? Well, if we know the full distance down the river is 8, and the distance between C and D is X, then this distance left would be labeled H, the total distance, minus X, the distance between C and D. So the distance between D and B would be 8 minus X. The total distance, subtract the distance between C and D. Now, if we take a look at our red lines, if we take a look at our red lines on the picture, we can see that we have a triangle. We recognize that triangle. It helps us come up with that formula when it's a right triangle. And we know it's a right triangle because they did specify that we're starting here at A and directly across the river at C is directly across, so that we know that's straight, and we are assuming the river is perpendicular to going directly across the river, creating a right angle. So we know that between A and C, that's a given amount. That's 3 kilometers because that's the width of the river. And we know that this distance between C and D is X. We don't know how far it is. And we have a hypotenuse here. Okay, the diagonal is typically labeled little c, but maybe I should label it something else because we have big C already used. So let me label it hypotenuse. So we'll label it hype. Okay, so we're trying to come up with as many formulas as we can because we're not exactly sure what we need. So let's see, what else do we know? Well, we look at the picture, this is the distance between A and D. That might be helpful. So let's solve for the hypotenuse here. Our hypotenuse, which is the distance between A and D. Okay. Distance between A and D, where this distance between A and B is the hypotenuse. Let me read that. Hold on. Give myself some more room. So the distance between A and D is the hypotenuse. So that means that we have the hypotenuse squared is equal to 3 squared plus x squared, which is 9 plus x squared, and we square root the hypotenuse to get the distance between A and D is equal to the square root of 9 plus x squared. Okay. So let's think about what we're trying to do. We are trying to minimize this time, the time, I believe. So I momentarily forgot. What the heck are we doing? If I go back to the problem, if you go back to the problem and take a look, they are asking us to quickly as possible. So we are trying to get there as fast as possible. And what we have is a rate that he rose. He rose at 6 kilometers per hour. So his row rate is 6 kilometers per hour, while his run rate, how fast can he run, not but run rate, they said was 8 kilometers per hour. Okay, so we have those as our time. We have a couple other distance formulas going on, and we are trying to minimize time. So we need to really go back to our algebra days. And I know you guys probably hate when I say that, but back in algebra, we learned that distance is equal to rate times time. A distance is equal to rate times time. D equals RT. And if we were doing work rate, so we also learned that work done, when we did this as an application problem in algebra, work done is equal to the work rate, how fast the worker can do the work, times the time it takes them to do the work. Okay, so this is all relevant here because if we're talking about a collaborative work rate, the collaborative work rate or a total work rate, actually we should translate this to a work rate first. So if many times we have to actually do this in terms of rates. And so we would divide by time. Actually, I don't want to do that this time because we're trying to create a formula that is a time formula, because remember we're trying to minimize time, so we need an equation that says time equals. So if we divide by work rate, WR, divide by work rate, then we get an equation that says, okay, the time it takes to row will be calculated by, in our case, we'll use the distance because we're talking about distance, not work. So we're going to take the distance and we'll divide by the rate. The distance divided by the rate will give us the time it'll take us to do that particular activity. Okay, so we have that. And we have all of the other formulas that we've created. Let's try to put some things together. Now, we are trying to come up with a total time that we want to minimize. Now, this time is going to be made up of the time we are rowing, so our row time, and plus the run time. In some cases, there are no run times because if we went directly from A to B, there's no run time. It would be all rowing. But is that the best way to go? Or can we get there faster if we stop at C and run the rest of the way, or stop at some point D and run the rest of the way? So if we take a look at our row time, now we just said that, let's see. We said that from A to D, D being any point between C and B. You know what? Let me draw this picture again because I want to explain something. We have A here, directly across we have C. And we have some point D somewhere between C and B, with our destination to be at B. Now we said that the distance between X and The distance between C and D is x, and the distance between D and B is 8, the total distance between C and B, minus x, what's already been done between C and D. Now, if you look at it, D is supposed to be any point. So that means it can be anywhere on this 8-kilometer stretch. So if x is 0, that means D is C. And if x is H, that means D is B. So essentially, if we just focus on D, we can accommodate all three scenarios by letting x be different values. So again, C would equal D if x is 0. Okay, because if x is 0, then D is the point C. If x is 8, then B is the same as D if we say that x has to be 8. Okay, and if x is anything in between 0 and 8, then it is some other point on the river. Hopefully that helps see where we're going with this. We need to now come up with this row time. And this row time, we're talking about rowing from A, and we just said that we can come up with all three scenarios by talking to D. So row time is that hypotenuse in the picture. So if we are talking about A to D, that distance, recall the distance from A to D was the Pythagorean theorem, x squared plus 9. That's our row distance. And row time, we just solved that time is equal to distance divided by rate. So our row time is going to be equal to the distance square root of x squared plus 9 divided by the rate that he rows, which we're told is 6 kilometers per hour. So that is our row time formula. Now we have the task of coming up with the runtime formula. Hold on, erasing. They don't make the erasing very easy. And if they do, I haven't figured it out yet. Okay, runtime. We have decided that the runtime is equal to the distance that you'd be running over the rate that he can run. So recall in the picture, here's A, here's C, here's D, and here's B. This is the row time, and wherever he stops off of rowing is the run time in red. So this, recall, the distance between D and B, we said was the total distance A minus X, which represents the distance between C and D. So that's the distance, 8 minus X. And we were told in the problem that he runs at 8 kilometers per hour. So there's 8. Or do I have those backwards? Nope, I don't. I think I have those right. Okay, so now that we have both of our equations, let's put it together. Our total time that we're trying to come up with an equation for, so we can minimize it, is a combination of our row time plus our run time. And we just found that the row time is square root of x squared plus 9 divided by how fast he rows, 6 kilometers per hour, plus the run time, which was 8 minus x divided by 8 kilometers per hour, which is how fast he runs. So this is our equation, our total time equation. Now that we have a total time equation written in terms of x, and that took us a while to get there, but I wanted to make sure you had all the pieces to the story in front of you before we filled in all these equations and you had no idea where they came from. We're going to follow our rules. The hardest part is interpreting the English and coming up with an equation. Once you have the equation, you follow your steps like clockwork. So once we have an equation that we want to find a minimum or maximum for, we take the derivative and set it equal to 0. So let's do that now. So we have total time. Okay, I'm going to call that total time is tt is equal to the square root of x squared plus 9 divided by 6 plus 8 minus x over 8. We take the derivative of this. This is not going to be the prettiest derivative, right? So we need to rewrite the square root in exponential form because you know that we can't take derivatives with square roots. And I can actually rewrite this divided by 6 as a 1/6 in front, which I think is going to be helpful when we're doing the chain rule for that. And same thing for here. I'm going to rewrite the divided by 8 as a 1/8 in front to help with our math there. So because this one doesn't have an exponent, I'm just going to take this 1/8 and distribute it through, which will make my derivative even easier to do. So rewriting, we have 1/6 times x squared plus 9. And actually, get rid of that because we haven't taken the derivative yet. We are just rewriting right now. Squared. Distribute 1/8 times 8 is 1. And 1/8 times negative x is negative 1/8 x. Now let's take the derivative. So this first part is going to be a chain rule. So we take the 2, we multiply it by the 1/6, and we get 2/6. Leave the inside function alone. Go back up, subtract 1. So that's an exponent of 1. And multiply by the derivative of what's inside, which is 2x. The 9 is a constant, so that goes to 0. Then we take the derivative of 1. And that is 0, so that part goes away. And the derivative of negative 1/8 x is going to be negative 1/8. Put a minus sign here, minus 1/8. Okay, so we have our derivative. And we can reduce this 2/6 to 1/3. So this is going to become 1/3. And actually, this is going to become 2/3 if I put this 2 in there. So 2/3 x times that is what that is going to look like. One moment. Notes gave me something different, but I'm not sure. They did. I think I'm okay here, unless you guys come back and tell me that there's something I missed, but I believe we are good. That's 1/3, 2/3. Okay, so we are going to have an equation of the derivative. Total time derivative is 2/3 x times x squared plus 9 minus 1/8. All right, we know that once we find the derivative, we are going to set it equal to 0. So we have 0 equals 2/3 x times x squared plus 9 minus 1/8. And we are solving for x here, so we probably should, let's add, okay, I think I know what I'm going to have to do here. Let's add 1/8 on both sides. And so we have 1/8 is equal to 2/3 x times x squared plus 9. Missing something? Oh, I know what I did wrong now. Oh, goodness. Okay. You guys would have caught this for me in class. Let's redo that derivative because I rewrote the square root incorrectly. When I rewrote the square root into exponential form, I squared, I think, or I did something crazy. It should have been a 1/2, and I didn't do that. So if we go back to the original equation, my apologies, let's go back to that total time equation. Okay, so that total time equation was the square root of x squared plus 9 over 6 plus x, nope, just kidding, plus 8 minus x over 8. Now, when I rewrote this square root, that's where I made my mistake. I didn't put raised to the 1/2 power for whatever reason, and that's why I was wondering why my answers were different from my notes. So let's rewrite. Let's again put the 1/6 out in front, but this time it's going to be x squared plus 9, not squared like I did originally by accident. It's supposed to be to the 1/2 power. And let's put this 1/8 in front. And we're going to distribute that through because it's going to make our derivative easier like we did before. So we're still going to want to distribute this 1/8 in. We're pretty good there. All right, so if we final setup ready for the derivative, 1/6 times x squared plus 9 raised to the 1/2 power, not the square, plus 1 minus 1/8 x. Okay, now we're ready for the derivative. Actual derivative. We take this 1/2 and we will multiply it down in front, giving us 1/12. And we keep the inside function the same for the chain rule. Don't touch it. Come back up, subtract 1 from 1/2 gives us a negative 1/2. Huge difference. Then multiply by the derivative of what's inside, which is still 2x. Derivative of 1 is 0. Derivative of negative 1/8 is negative 1/8. Okay, this looks better. So now if we simplify on this next slide, what's going to happen is this 2 times 1/12 is going to equate to 1/6. And this negative sign here is going to create the square root to go back to the bottom. So let me write this back out. So we have the derivative that we just found for total time is 1 over 12 times x squared plus 9 raised to the negative 1/2 power times the derivative of what's inside 2x minus 1/8. If we simplify a little bit, find 2 times 1/12 gives us 1/6. And we take this negative exponent and make it positive by bringing it down. We have 1 over 6 times the square root of x squared plus 9 minus, actually, an x here. So that x is going to stay in the numerator. The 2 and the 12, the 2 divided by 12 gave us the 1/6. So that's why this 6 is down here. Then we just subtract that 1/8. Okay, now we're ready to set this thing equal to 0 now that we have it all simplified. So we have 0 is equal to x over 6 times the square root of x squared plus 9 minus 1/8. So let me add 1/8 on both sides. And we'll move on to the next slide to see that. Okay, so we have 1/8 is equal to x over 6 times the square root of x squared plus 9. Now let's get rid of this fraction by cross multiplication. So we have 6 times the square root of x squared plus 9 is equal to 8x. Let's divide by 6 on both sides, which leaves us with the square root of x squared plus 9 is equal to, and we just divided by 6. So 8 divided by 6 reduces down to 4/3. So we have 4/3 x on this side. Okay, where do we go next? Well, let's get rid of this square. So let's square both sides. I mean, get rid of the square root. So we're going to square both sides to get rid of that square root. We have x squared plus 9 is equal to 4 squared is 16, 3 squared is 9, and then x squared is x squared. Now we can see that we now have two x terms, but they're both x squared, so this is going to make our life so much easier. Let's now let's subtract x squared on both sides. So if we think about this, what we're really doing is we're taking 16/9 and subtracting 1. In order to do that, we need 16/9 minus 9 over 9. 9 over 9 is the same thing as 1, but just written. So we can actually subtract the fractions. And 16 minus 9 is 7/9. So this gives us 7/9 x squared on the right side and a 9 still on the left side. So we have 9 is equal to 7/9 x squared. The last step is to multiply both sides by 9 over 7. It's the reciprocal of this fraction so that the 9's cancel and the 7's cancel, leaving us with just x squared. And on this side, we have 81 over 7. Okay, so now we have 81 over 7 is equal to x squared. And to get rid of the square to finish this off, we have square root. Yes, technically we do plus or minus, but in these application problems, we aren't talking about negative time. We're not talking about negative distance, so it would make no sense to use the negative version. So we have x, which remember, x represented the distance between directly across the river and where he's actually going to land. And we have found out that he should row square root of 81, which is 9, over the square root of 7, which is not an even square root, so just keep it. He should row 9 over square root of 7 kilometers down the river before he switches to running. So if we find approximate answer, we do 9 divided by the square root of 7 in our calculator, we get that this is approximately 3.4 kilometers down the river, and then he should run the rest. Okay, so if we want to know what the rest is, we take 8 and subtract 3.4. So 8 minus 3.4 leaves us with 4.6 kilometers that he's going to run. So he is going to row 3.4 kilometers downstream. Well, actually, no, that's not true. He's going to row diagonal, so we don't know that length yet. So if we draw a picture, pictures would be helpful. Let's do that. Numbers on our screen. That's a long one. So here we are. He starts at A. He wants to go to B. He can go here or he can go anywhere here. We just found that X, how far down he should go, where he should stop at D, is 3.4 kilometers downstream. And then we found that he'll be running a remainder of 4.6 kilometers. So this is the actual run distance, not rum. I don't know why I keep doing that. The run distance, because he's running straight down. Now he's not rowing straight from C to D, so 3.4 is not the actual distance that he's rowing. We have to think of that right triangle again. Okay, so 3.4 is X. We know the width of the river is 3. So what we really want to find is this distance here, which is the distance he will be rowing, the hypotenuse. So we go to find the hypotenuse by using the Pythagorean theorem. Let's do that now that we have 2 out of the 3. And we said that the distance between A and D was the formula, the square root of x squared plus 9. Okay, so now that we know x being 3.4, we have the square root of 3.4 squared plus 9. we put that in our calculator, square root 3.4 squared plus 9, all under the square root, we get that the distance he'll be rowing is 4.5 kilometers approximately is how far he will row. Okay, so now we have the rowing distance and we have the running distance, and we can say that in a conclusion that he should row from A to D for 4.5 kilometers. Then run from D to B for, and I believe we said that was 4.6 kilometers. Essentially, half of his distance he should be rowing, and half of his distance he should be running. And we could figure out the time, but I don't believe the problem actually asked for that. I believe it just asked for what path he should take. The problem said he wants to get there as quickly as possible. Where should he land to reach B as soon as possible? Okay, so we are stating that he should land from, write down all these numbers, 9 divided by the square root of 7. He should land 3.4 kilometers downstream, which means that he'll be rowing for 4.5 kilometers across the river before he runs for 4.6 kilometers down. Whew, that was a long problem. I'm sure you guys felt the pain as much as I did, but hopefully you can learn from my mistakes that I have, and you can use these examples to help you through the classwork. Okay, remember, I am definitely accessible through email, and we can set up a live chat. If my email solutions for you do not work, you just let me know and we'll set this up so we can do some problems together.